Okay, so I'm going to start talking about wake and sleep cycles. Really these rhythms that we have throughout the day for staying awake and falling asleep, and what's really happening when we're asleep. And I'll probably maybe pound it into your head more than you want me to. The importance of sleep, as I have learned how important sleep is.
As we're going to talk about how we have these circadian rhythms, so rhythms that occur about every day, circa 80. He starts out, Callatt starts out talking about how many animals, I feel like most animals, generate endogenous circannual rhythms. I think even we have some hormonal changes that occur during spring, a lot of things that are less obvious than what we see as far as animals who hibernate through the winter, animals who store food for the winter, that they start this relatively early on. And I like the example of birds' migratory patterns because, or the butterflies' migratory patterns, because it's clear that for them to come south for the winter, that it might need to get cold up there, but that's not actually what's happening. They have internal mechanisms that are operating on this annual cycle, and they are driven and so to go south for the winter, and so they're driven to go back north. There's nothing specific about the weather necessarily that tells them they need to go north. They know it's time to go north. And all animals have these endogenous circadian rhythms. So endogenous is generated within ourselves, right? That these internal mechanisms that operate on an approximately 24-hour clock, not an exactly 24-hour clock. So there are other aspects of our world that help us to reset our cycles. The most clear cycle that we have is wakefulness and sleep. But you'll notice that there are times during the day when you're in a better mood or in a worse mood, that you are more likely to eat and drink. Your body temperature changes. Probably don't notice that, but your body temperature changes throughout the day. Hormones, sensitivity to drugs, urination, all of this is also influenced by these endogenous cycles. And even in the absence of whatever changes are occurring throughout the day, daylight, we can see consistent rhythms of activity and sleep. Your author gives us the example of, I think this is a flying squirrel, and that is kept in the complete dark, and then they're watching the waking cycle. The dark blue lines there are the waking cycle, and you can see that that flying squirrel is waking slightly earlier every day, so slightly less than 24-hour clock. But I've seen other examples. So mice on a running wheel that in the complete dark, they have a slightly longer, maybe almost 25-hour period. Your author gives us the example of people who are on a submarine appear to have about a 24.3, 24.4 hour period. And he also talks about people who live in Antarctica, where there are times where there is no light, and how they can get irritable, of course, but they are drifting off of this endogenous cycle, or they're drifting off from the 24-hour day cycle in an individualistic kind of manner. So as I said, other aspects of our lives are influenced by these endogenous cycles. One is body temperature, and he shows here how we have our highest body temperature really probably late in the afternoon, and then as we get to sleeping and onset of sleep, it's usually about 2 in the morning, 3 in the morning, that we have a really low body temperature. We also see an effect on our mood of these endogenous cycles. So this comes from a study where they had students come in, they kept them under constant light levels and kept them awake for 30 hours. They either came in at 10 a.m. or they came in and started at 5 p.m. And you can see that regardless of what time they started this study, that people said their most positive mood was on average around 5 p.m. and their most negative mood was on average around 5 a.m. Our endogenous cycles change. a bit over our lifespan, and actually we see that in other animals as well, that their cycles change as they age. As when we are very young children, we tend to go to bed early and wake up early. So he has here starting at 10 years old, or midpoint. So what's on the y-axis there is the midpoint of the night. So 3 a.m. would be, I went to bed at 10 and woke up at 8. This gets later and later, and you see this peak right around late adolescence, and then we start to get slowly closer and closer. If you know how your grandparents work, they're doing something that looks a little bit more like children, of going to bed pretty early and getting up pretty early. And after, they tend to start sleeping less and less, so they're going to bed early and waking up very early. This change, where we see adolescents tending to stay up late and wake up late, this occurs in other species as well, which I think is rather interesting. And I have seen one person talk about this where he also shows this dip that we tend to have in our circadian rhythms after lunch, that adolescents just don't have that. And if we let them, they would have this kind of longer clock. Things that affect these biorhythms are called zeitgebers in the German for time giver. Sunlight is a major zeitgeber for humans. It's actually a major zeitgeber for land animals. The tides are a stronger zeitgeber for marine animals, and those are the strongest zeitgebers. We also have other things about our lives that affect these rhythms. So physical activity, if you've ever heard that you probably want to do your physical exercise early in the morning, or at least earlier in the day. You don't want to do the physical exercise in the evening, as it'll tend to keep you awake. Eating, temperature outside, sleep-related hormones, these are all also zeitgebers. We have our free-running circadian rhythm, as I mentioned before, that we have a slight drift from the 24-hour clock if daylight is not a factor, which I mentioned for the submarine workers and for the people in Antarctica. But we see this again with other animals as well. If we use something other than sunlight as our zeitgeber, it tends to lead towards depression, irritability, and impaired job performance, as we will see when we talk about shift work. We can see clear effects of how light affects us as a zeitgeber. This kind of study has been done in several countries, but these data are from Germany, where you can see the y-axis is the midpoint of sleep again. And if we look at so all of Germany is in a single time zone, but what's happening in the west, right, is that the sun is coming up later and going down later than in the east. And if we ask people if they were just allowed to go to sleep and wake up when they wanted to, when would that happen? We see that their midpoint gets earlier and earlier as we move towards the east, where the sun is coming up earlier and going down earlier. When talking about setting and resetting the biological clock, it's good to talk about jet lag, as it brings this to bear. When we change time zones, we have a real mismatch, right, from our internal circadian clock of what we're typically on and where we are, and the external time in the world. As if you've traveled, you realize that going east is much more difficult than going west. Going east causes this, what they call a phase advance. So if you think about it, if you are a person who sleeps from 10 p.m. to 6 a.m. and you go from the West Coast to the East Coast in the United States, this is now you are feeling like you have to get yourself to sleep by 7 p.m. It's difficult. You have to get up at 3 a.m. and we all know how hard that is. I stole this picture from Laura Freeberg's physiological psychology textbook, because I like the clocks and that it helps us think it through. I also like the smiley faces and unhappy faces. So going east, we have an unhappy face, as we are forcing ourselves to bed and getting up extremely early is how it feels. Whereas going west is what they call a phase delay. So if I sleep from 10 to 6 typically, now it's going to feel like I'm just have to push through to 1 a.m. and stay up. And that's not too hard to do. And then I get to sleep in until 9. So going west is much easier. Your author here, and most of the authors I've read, talk about stress and the effect on cortisol levels of changing these time zones very much. So when we change time zones, we do see a raise in our cortisol levels, and if we're doing this a great deal, this gets to be a pretty consistent raise in cortisol levels, which can be really deleterious. So they have a study looking at flight attendants who cross time zones, and they have found that these people have smaller than average hippocampi. So where we lay down our new explicit memories from this kind of consistent raise in cortisol levels. And as I mentioned before, when we're using something other than light as a zeitgeber, that we have some depression, some irritability, and poor job performance. If we look at shift workers, night shift workers tend to sleep more poorly, feel groggier at work. Their body temperature is continuing to peak as they are sleeping. If you go back to that body temperature figure, that's really somewhat based on daylight, not just our sleeping schedule. So that's working against each other. They tend to have more accidents than day shift workers. He does mention here that if we have truly blackout curtains and can sleep in the dark, and if we are working in a place where the lights are truly giving us some sense of sunlight, that they're really strong lights, that can help. And here are figures showing that the daylight saving change when we spring forward, so we have that same kind of phase advance that we saw when going east. We actually see that this correlates with more heart attacks. If you look at the Tuesday after the spring forward, so when we go back to work on Monday, the Tuesday after, we have significantly more heart attacks than other days. And if you look at the fall back, so the phase delay, we are doing a little bit better on that Monday morning in the B figure. It was Kurt Richter who introduced the concept of the brain having its own kind of biological rhythm, that it's the brain that is influencing our biological clock. And we have discovered that this is happening or occurring because of the suprachiasmatic nucleus of the hypothalamus. That's a fun bunch of words that you can say. It's a mouthful. You can say it again and again with your friends. Suprachiasmatic nucleus of the hypothalamus. Suprachiasmatic nucleus of the hypothalamus. You can shorten it to SCN, but the nomenclature is great. Supra on top of, chiasmatic on top of the optic chiasm. So we have these retinal ganglion cells in our eyes that are going to send information about the relative light to this area of the hypothalamus, and helps us to control and reset our circadian rhythms for our sleep and for body temperature and everything else and so forth. This continues when removed from the body. So they have taken cells from the suprachiasmatic nucleus of the hypothalamus and put them in tissue culture, and they continue to have their same biological rhythm. And the more cells that they take, the stronger that rhythm. One of the studies that has looked at this looked at hamsters, and so there were these hamsters that genetically had a 20-hour biological clock. Most hamsters, or like most mammals, have about a 24-hour biological clock. But so they took these hamsters, the fetuses of these hamsters with a 20-hour biological clock. They actually did this in both directions. They surgically transplanted just the suprachiasmatic nucleus of the hypothalamus from the fetuses into adult hamsters that had a 24-hour biological clock, and it changed those hamsters' biological clock to be a 20-hour biological clock, and vice versa. They've taken the 24-hour hamster fetuses, SCNs, and transplanted those. So it's the donor that's important here. So as I just mentioned, there are certain retinal ganglion cells that are responding to light, and they are sending their information to the suprachiasmatic nucleus of the hypothalamus. And they are doing this along what's called the retinohypothalamic path. And this pathway is named, as many of the pathways are named, of where it starts in the retina and where it ends at the hypothalamus. And this, again, is going directly to the suprachiasmatic nucleus of the hypothalamus so that light can help us reset our internal biological clock. These retinal ganglion cells have their own photopigment. If you remember, the photopigments were in the rods and the cones. We had rhodopsin in the rods, but these retinal ganglion cells have their own photopigment called melanopsin, and they respond slowly. So they're responding to, I want to say, ambient light levels, or where you are generally in light levels. If you have a sudden burst of light or darkness, that's not going to affect them. So if you have to get up in the middle of the night and go to the bathroom and you turn on the lights, that's all fine. It's these, when you're in the light for a while, we'll see a change. So this is a nice picture of showing the, so in A, the suprachiasmatic nucleus, he's pointing to it there, that it is active in the daytime. So this is one of those studies where they injected 2-deoxyglucose to see what brain areas were active. And A is showing us in the daytime, the SCN is very active, and B is showing us at night, it is not active. And we're going to see the suprachiasmatic nucleus of the hypothalamus is actually communicating to other areas to influence our sleep-wake cycles.
So the suprachiasmatic nucleus of the hypothalamus, say that 3 times fast. So the SCN regulates waking and sleeping by controlling activity levels in other brain areas, and particularly the pineal gland, this small gland in the center, kind of really in the center of the brain, just posterior to the thalamus. It releases the hormone melatonin. Melatonin is secreted at night, so when the SCN is turned off, we are secreting melatonin. And this is how the brain works. And for us, because we are diurnal animals, this makes us sleepy. But if we were nocturnal animals, melatonin, the SCN being turned off, allowing the release of or secretion of melatonin would make them more awake.
Sleep is a state that our brains are actively producing, where we see a moderate decrease in brain activity, this kind of slow decrease, and then another decrease, and also a decreased response to stimuli in the world. The electroencephalograph, that was invented in 1929, and it was the thing that allowed researchers to discover that there are various stages of sleep. A lot of the research was in the 50s and 60s with the original kinds of discoveries using the electroencephalograph, and it allowed us to see that we have different brain activity during different times of our sleeping state. This picture is showing somebody who is doing a sleep study. One thing that they use is called a polysomnograph, where they are looking at the EEG, so the electroencephalogram, and eye movement records to see what's happening at different stages of sleep. Oftentimes what you'll see here is she has something taped to her chin there. They also get oftentimes an electromyogram. So this is measuring muscle activity. Okay, I'm actually providing the polysomnograph that is provided in your textbook over on the left, and then another recording of EEG over on the right, because there are a few things I'd like to talk about with all of this, and each of these shows different aspects of all of this. So when we're relaxed and awake, we have what's called alpha activity. If you remember doing that meditation, that short silence that you had, you most likely, or if you're kind of in class and you're maybe just really relaxed and maybe almost falling asleep, when we're really relaxed, we have this alpha activity. It is at 8 to 12 hertz, so 8 to 12 cycles per second. When we're awake and we're busy, like busy thinking about something or doing something and active, we have slightly faster brain activity at 13 to 30 hertz. You don't need to know the how many hertz or anything, but I'm just letting you know. So this is a faster activity, and what that activity is showing us is neural crosstalk, so neurons chattering at different times than each other. Okay, so that is in A, and then the alpha and beta is at the top of the one of the EEG on the right.
As we're falling asleep and we're into stage 1 sleep, we get into theta waves. So now our brain activity slows down. We have this moderate decrease from 3.5 to 7.5 hertz. Okay, and we see that kind of continue on into stage 2 sleep. As we're getting into stage 2 sleep, we tend to see that same kind of theta activity, and it's kind of irregular, and mixed in with that are these sleep spindles and K complexes, where the sleep spindles are these fast bursts of activity at about 12 to 14 hertz. It looks like, so very interestingly, I think, that we have sleep spindles somewhat throughout the night, but mostly in stage 2, and that they are correlated with nonverbal IQ scores. So the more we're having sleep spindles, the higher our nonverbal IQ. They also appear to be helping us with memory consolidation. As we see, we need sleep in order to consolidate our memories. If we look at the K complexes, this is really a sharp complex in the waveform that we have about 1 per minute here in stage 2 sleep, but it's also triggered by noises or external sounds and things that might wake someone up. So it is suggested that this is really the brain's attempt to stay asleep. Okay, as we move into stages 3 and 4, we see more delta activity. So delta activity is getting down to less than 3.5 hertz, and they used to distinguish stage 3 from stage 4, where stage 3 is about 25 to 50% delta activity, and stage 4 is over 50% delta activity. But they're very difficult to distinguish from each other, and now they really just lump those two together in that kind of, and they call it slow wave sleep. And what we're seeing there with this much slower, many fewer cycles per second, this much slower neural crosstalk, is that what's really going on is the neurons are quiet, and then they are communicating at the same time, and then they're silent and inhibited at the same time. This kind of synchrony. And that's when it looks like our brains are really getting the rest that our brains need. And then this final stage in F there in the figure on the left is REM, or paradoxical sleep, as it's considered paradoxical because in some ways it looks like we're awake again. And so if you see over in the right, he's marking this as some of its theta activity and some of its beta activity. It actually looks like we're awake and busy. So this is when we are dreaming. There are other times when we are dreaming, but this is when we're having those really usually more strange dreams and things, and kind of storyline to our dreams. What you can also see, so in the polysomnograph, what you can also see is that there are eye movements during this paradoxical sleep, which the REM stands for rapid eye movement sleep. All of the other stages together are considered to be non-REM or NREM sleep. So REM sleep, or paradoxical sleep, does have the two names. It is one of those things that was discovered at about the same time in 2 different labs. And so Michel Jouvet was working with cats. He was examining cats after the removal of the cerebral cortex, and he was noting their paradoxical sleep, that it was paradoxical in that it was like a deep sleep in some ways, but like a light sleep, or almost like we're awake in other ways. Our US team that named rapid eye movement sleep as REM sleep, or rapid eye movement sleep, they were recording eye movements at the onset and offset of sleep, and they were turning off their eye movement recording machine at night because they didn't want to use the paper. It was expensive, but occasionally they would turn the machine on. And then they noticed during REM sleep that there were these eye movements. They actually thought this was a mistake, and did several iterations of examining the rapid eye movements during sleep to make sure this is really what was happening, because that was not what they expected. So we have rapid eye movements. We have a mixture of theta and beta activity, so some relatively fast activity, quicker activity than when we're in slow wave sleep, but then fast activity like we're awake and busy. As we are dreaming, we are apparently, what it looks like with the eye movements is that it looks like our eye movements are moving as if we're watching what's happening in the dream. I think if I remember correctly, someone was telling them they watched a bit of a tennis match and they could see the eye movements go back and forth after when that person was reporting on what their dream was. So it's their suggestion that we are watching what's going on in our dreams. We also have inhibition of the large muscles, so our muscles are very relaxed. We have fluctuation of breathing, fluctuation of heart rate and blood pressure, facial twitches. This is why we have that electromyogram to tell us about that muscular movement. We also see during REM sleep erection in males and vaginal moistening in females. I have a couple of figures on this slide. The one at the top right is showing the number of hours of sleep. So as someone is sleeping, we're watching them across time. One thing you'll see is that it takes us about 90 minutes to get into REM sleep. And what we're doing is we go stage 1, stage 2, stage 3, stage 4, stage 3, stage 2, REM sleep, stage 2, stage 3, stage 4. And we start skipping stage 1. That's really just as we're first getting to sleep, as stage 1. And as we are spending more and more time asleep, we're spending more and more time in REM sleep and less time in slow wave sleep. And that is shown for several people. So in the bottom figure, this one is from your book. They're watching the sleep stages at night, and we can see those darker blue areas that are showing us the slow wave sleep. We have more of those early in the night. And then if we look at the really, really light blue areas that are very pale blue, the REM sleep, we're having more and more of that as time goes on, the longer that we are asleep. As I said, what's going on with slow wave sleep and those delta waves is that we have synchronized neural activity and synchronized inhibition of activity. And this appears to be when our brain is really resting itself, basically. And I liked the figure to the right that really shows this is an off time versus an on time, and this is happening more slowly than what we see with that neural crosstalk, which is a really fast kind of neural communication.